So in this video, we're going to review the types of bonds and also discuss electronegativity and how it determines bond polarity. So first to review, anytime we have atoms coming together, we can essentially have two types of bonds. We can have ionic bonding or covalent bonding. So ionic bonding is when you have a metal and a nonmetal coming together and they have already exchanged electrons, or the metal has lost electrons and the nonmetal has gained. And now these two are bonded together electrostatically. So the ions, the charges are just being attracted to each other through the electrostatic force, if you will. Whereas covalent bonds, we have two nonmetals coming together. So here we have oxygen and hydrogen. Both of those are classified as nonmetals. They're sharing the electrons here. Here with ionic, they're not sharing. So that's just a review. I can't write sharing. Not sharing the electrons. Those are the two types of bonding that we essentially have. And then just to review on how we get ions in the first place, so we introduced this term called cations. Cations are formed when an atom loses electrons, so that's essentially what happens with metals. And they're doing this to basically achieve a noble gas configuration or a complete outer shell of 8 electrons. And then we use this term isoelectronic to say that they have the same number of electrons or the same electron configuration as another element, in this case, a noble gas. And then the example here is magnesium. Magnesium is in the second column of the periodic table, and all of the elements in the second column from the left lose 2 electrons. It's losing its 2 valence electrons, its 2 electrons on the outermost shell, to have a 2+ charge. So anions are when a nonmetal gains electrons, and it'll become negatively charged because then it has more electrons than protons in the nucleus. And same thing, it's doing this to become isoelectronic with a noble gas, to have the same number of electrons as a noble gas. It's having a complete outer shell, a full complete octet essentially. And so our example, chlorine being in that 7th, well, it's actually the 5th one you're looking at the P block. It's group 17 by this nomenclature, but it's essentially, it has 7 valence, so it just needs 1 more. So if it just gains 1 valence electron, then it'll have a complete outer shell, and that's why chlorine is a -1 charge. So just a quick discussion on ionic radii, because this will have to do with bond length when we get into that next. But anytime you have a metal, so like sodium here, lose an electron, so we went from neutral to a +1 charge, it's losing that outer shell, so its radius gets smaller. So notice its radius went from 0.186 nanometers down to 0.095. So these metals will get smaller when they lose electrons. And then what we saw in the other, with the nonmetal, the chlorine. So chlorine going from neutral, it gained 1 electron to become an ion. This one, it got larger when it gained electrons. So this is the trend of what happens. Anytime you have a cation losing electrons, it's going to get smaller. Anytime you have an anion gaining electron, it's going to get a little bit larger. Now, for the metal, this is due to it losing a full outer shell. For the chlorine, for the nonmetal, it gets larger due to what we call electron pair repulsion. So recall that electrons are negatively charged, and we know that opposites attract. A positive and a negative will be attracted to each other. If we have 2 negatives trying to get close to each other, they're going to repel each other, and that's essentially, in a nutshell, what happens when you have a nonmetal going from neutral to charged. You have more electron pair repulsion, and that just makes the whole thing a little bit larger. Now with covalent, this was essentially talking about ionic. With covalent, we have something very similar. So we can still talk about the size of atoms and the size of ions and how that affects essentially bond length. So when a covalent bond forms, the valence shells of the 2 atoms are pretty much overlapping a little bit, which is why they draw the molecule like this. So here we're showing the valence shell of the hydrogen. Here we are showing the valence shell of the chlorine, and they do overlap a little bit, again, because those electrons are being shared, which is why we draw our space-filling model of an HCl molecule like that. Now we're talking about, again, this is the 1s of a hydrogen, and the 3p of a chlorine. So why is it 3? Why is it 3p? Take a look at where chlorine is located on the periodic table, and that'll answer that question for you. And then bond length is essentially the internuclear distance. So the distance between the two atoms, or specifically between the two nuclei. So that distance is called your bond length, and that has implications in terms of how strong that bond is. For ions, we could have a very similar conversation, but that's going to be also based on the radius, but here they're not overlapping. So going back to this picture, see how we don't draw the two ions overlapping? That's because they're not sharing the electrons, they actually transfer the electrons. It's just the two charges being attracted. Here, the valence electrons are being shared, so the valence shells are overlapping, which is why we draw covalent molecules a little differently than the ionic ones. So then bond energy is very closely tied to bond length. Energy is released when two atoms form a bond. So it's a misnomer or a misconception to say that energy is stored in bonds. Actually, what happens is energy is released when a new bond forms. So for example, we have hydrogen and chlorine as two separate gaseous atoms, and then we form a single new molecule, and then we have heat written over here as if it was a product, as if it was a molecule. But it's just here on the product side. It's not actually a molecule, but it's acting like it's a product because we get heat. And then the opposite is true. Energy is going to be needed to break a bond. So if energy is released when a new bond's formed, energy is needed to break bonds. So breaking bonds requires energy. Now, the energy required to actually break a bond, we're going to call the bond energy. So if a covalent bond is said to have more bond energy, that means more energy is going to be required to break that bond. The amount of energy required to break a covalent bond is the same amount of energy released when the bond is formed. So here, this reaction, it's just the reverse of the first one. And here, heat is written as a reactant because heat is required to break this bond that's between the hydrogen and the chlorine. So breaking bonds requires energy, and forming bonds releases energy. So next we're going to get into Lewis structures, electron dot formulas, and they're essentially the same thing. The book and the slides are calling it electron dot formulas. It's for the most part the same as what we call Lewis structures. It's just drawn slightly differently. So we didn't do it in the slides, but in chapter 5, if you look at chapter 5, they talk about electron dot formulas for atoms. So for example, chlorine has 7 valence electrons. So that means we would draw the 7 valence electrons as 7 dots right around the atom. That's what they mean by an electron dot formula for an atom. The number of dots around each atom is equal to the number of valence. So you can pretty much just go from its location on the periodic table. So oxygen has 6. So we can just put 6 electrons around it. That would be the electron dot formula for oxygen. So what we're going to be doing now is doing electron dot formulas for actual molecules. So now we're talking about the atoms, or the atoms sharing electrons to form molecules. And then what we really call them, once we're done with these drawings, we call them Lewis structures, which show the bonds between the atoms. And the reason why this is useful is because if we can visualize the arrangement of the atoms in a molecule, we can make conclusions about the polarity of the molecule and the shape of the molecule, and ultimately what the physical properties of that compound have. So one quick thing that's going to come up with Lewis structures is this idea of resonance. So we might circle back to this, but resonance is essentially when we have a double bond in a molecule. And notice that with this example, they've got SO3, and they haven't finished drawing these, but when they arranged the atoms and started drawing lines to represent bonds, they could have essentially put this double bond anywhere. So here they put on the left, here it was in the middle, here it was on the right. Because they have, because we have the freedom to put this double bond in any of these locations, this compound has a phenomenon that we call resonance. And we're going to get into this and do some examples. So they're basically saying the double bond could have been placed between any of the 3 oxygens. So the Lewis structure could have been drawn any of these, and that's called any of these ways, and that's called resonance. So first example, we're going to do electron dot formula, and we'll translate it to a Lewis structure for NH4, which is ammonia. So the first step that you have to do anytime you're doing any Lewis structure is count up the total number of valence electrons. So you get that from looking at the periodic table. So nitrogen, for example, based on its position in the periodic table, has 5 electrons, and then each hydrogen has 1 valence, and then there's 4 of them. So you take that entire total, you get 5, and then I don't know why, I don't like how they're using minus signs here because we're adding up electrons. But you have 5 electrons. This really should be a plus sign. But this one is indeed a minus sign. I'll explain that in a minute. So you have 5 electrons from the nitrogen, 4 from the 4 hydrogens, so 5 plus 4 equals 9. But they have 8 here, so how did they get 8? Well, notice that we've got a positive charge for this molecule. So the positive charge is because that this NH4 compound has an overall charge of plus 1. Electrons are negatively charged, so if a compound or an atom or an ion has a charge of plus 1, that means it must be deficient by 1 electron. So then that's why they have a minus 1 right here to bring it down to 8. So the point is that for this compound, NH4, we have 8 electrons total, 8 valence electrons, and that is step 1. Anytime you're going to draw a Lewis structure, step 1 is count up the number of valence electrons. Step 2, they've arranged the nitrogen, kind of put the nitrogen in the center, and then the hydrogens on the 4 sides of the nitrogen, and then put a lone pair, or essentially a pair of electrons, it's not a lone pair, but a pair of electrons in between to form what is basically a bond. So the 4 electron pairs around the central nitrogen, they're attaching to the 4 hydrogens and essentially making 4 bonds. So a Lewis structure way of drawing this, I'm going to draw it over here. So an N, H, 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 H. So a Lewis structure would look like this, where we simply have lines instead of dots. So the dot formula that they did on the previous page, they're putting 2 dots. A Lewis structure, the dots essentially become lines. And honestly, this is what we do on a day-to-day basis. This is kind of like the we're just learning way, and this is the real way of doing it, if you will. And then one thing that they also had on the previous slide is having brackets and then a positive charge. That is consistent. That is what we should also be doing because the molecule itself had a positive charge. So there are the brackets that they did. We want to keep on doing that. So that's what this step 3 is. Enclose the polyatomic ion in brackets. If you're talking about a neutral compound, so if we were going to do like ammonia, NH3, that doesn't have a charge, so we wouldn't have any brackets and a charge for that one. Let's do another example, or let's do an example where it's not charged, and then we'll come back and do the carbonate ion. So like CO2, for example. So step 1 is count up your valence electrons. So carbon, by the periodic table, has 4 valence electrons. And oxygen, each oxygen has 6 valence electrons, but there's 2 of them. So times 2, that's going to bring our total to 6 plus 4. So what is that? That's 12 plus 4, so 16 electrons total. Next thing that you would do is recommend putting the carbon in the middle. Usually the rule is you put the less or the least electronegative atom in the middle, and we'll review electronegativity in a bit, and then put the other atoms around it. And then we can connect these atoms with lines, where a line is basically 2 electrons. So with this one, if I asked you the question, how many electrons have you drawn already? You've drawn 4 electrons. We need to make sure we have 16 total when we finish our drawing. So we need to draw 12 more. And then remember the octet rule as well. So atoms want to try and have 8 electrons around it. So if, for example, we gave some double bonds between the carbon and the oxygen, notice that now this carbon essentially has 8 electrons around it because it has I can't change the color of my pen. Essentially, we've got 4 electrons over here and 4 electrons over here because a line is 2 electrons. So that means right around the carbon, we have 8 electrons, so the carbon is happy. He's happy because he has his octet. Now for the oxygens, and I can't erase what I've drawn, so I'm going to redraw it over here. The oxygens only have 2 electrons immediately around it. So if we kind of draw a little bubble around the oxygen, we've only got, sorry, not 2, but 4 electrons. Each oxygen wants to have 4 more. And if we just do a quick head count, we have drawn, with this drawing right now, we've drawn 2, 4, 6, 8. We've drawn 8 electrons. We need to draw 16 total, so we need 8 more. If we were to put lone pairs around the oxygens, that satisfies 2 things. Now the oxygens have 8 electrons, they have an octet, and we have brought our count up to 16. So we drew 8 more electrons to bring the total count of electrons in this drawing up to 16. I'm going to do another example. So let's do CH4 methane. So if we had to draw a Lewis structure for methane, step 1, count up all the valence electrons. So carbon, by its position on the periodic table, has 4 valence electrons. Hydrogens always have 1. And then there's 4 hydrogens, so that'll be times 4. So that brings the total to 8 electrons. So the next step, put an atom in the center. Carbon is pretty much always at the center. And when you get to larger molecules, it's a different discussion. But this carbon's going to be at the center. Hydrogens are never going to be in the center because they can only form 1 bond in the first place. And then we'll take the other atoms and spread it around the central atom. Next, we can connect these with lines. And then remembering that a line equals 2 electrons, if we just pause and count up how many electrons did we draw right here? Well, we've got 2, 4, 6, 8. We've got 8 electrons. I had to have 8 for my structure, so we're done. It's just a carbon with the 4 hydrogens around it. That is our Lewis structure for methane. I'm going to do one more example. So I'll do diatomic nitrogen, so nitrogen gas. So step 1, count up how many valence electrons should be in this molecule. So nitrogen, by its position on the periodic table, has 5 electrons, and then there's 2 of them. So that means we should have 10 electrons total when we make our Lewis structure drawing. So next up, now we only have got 2 atoms, so I guess I'll just put them next to each other and then connect them with a line. So then pause and ask yourself, how many electrons have I drawn? A line equals 2 electrons, so I've only drawn 2 so far, so I need 8 more. Now if I just take these electrons and put them around the nitrogens as lone pairs, maybe you can see the problem. These nitrogens do not have an octet, so there's no octet here. That's not good. We want all of our atoms in our Lewis structures to have octets if possible, with the exception of hydrogen that is just happy with a single bond. So what can we do to fix it? One thing we can do is take a lone pair from this nitrogen and make a double bond, and then take a lone pair from the other nitrogen and also put a bond in the middle. And what you end up getting is essentially a triple bond in the middle of those 2 nitrogens. So this is the answer for the nitrogen molecule. Now, one thing that you can do to practice this is take a molecule, or for any molecule that you are trying to draw a Lewis structure for, like from your homework, try to draw it where if you need to make double bonds and triple bonds in order to give all of the atoms an octet, do that, and then just Google the molecule with the word Lewis structure, and you can use it as a way to check your answer. So now let's go back to this slide and this is the carbonate ion. So the same kind of steps, and they're going to do electron dot, but I can redraw it to show you what it looks like as a Lewis structure. But again, first thing, find the total number of valence electrons. So for carbon, there's 4 based on its position on the periodic table. Each oxygen has 6 valence electrons, and then there's 3 oxygens. So we have 3 times 6, that's 18, plus the 4 makes it 22. And then here, this plus 2 right here comes from the fact that it has a 2 minus charge. So our examples that we had on the black slides, those were all neutral compounds, so I was not adding or subtracting extra electrons to accommodate the charge. But this carbonate polyatomic ion has an overall charge of -2, so whatever count we get, which was 22 electrons, we're going to have to add 2 more electrons to get 24 total to account for the fact that the molecule has an overall charge of -2. So here they say we must add 2 electrons for the negative charge. So then next thing is they put the carbon in the middle, oxygens around it, and once you start putting pairs of electrons in between, you would get something that looks like this. Now, I'd ask you, especially in the classroom, like, what's wrong with this structure? So if you look really closely, you'll see this oxygen right here does not have an octet. It is not happy. It does not have 8 electrons. The other ones do. This oxygen does, carbon does, and this oxygen has an octet, but this oxygen down here does not have an octet. So he is not happy. So one thing that we can do to remedy the situation is make a double bond. So on the previous slide, there was a lone pair right here, if you remember. They basically took that lone pair and made a double bond with this oxygen. So now this oxygen does indeed have 8 electrons locally right around it, and he is happy again. And then to finish off, because this thing was charged, we're putting it in brackets. So again, those 3 examples we did on the slides that were black, those were neutral compounds, no overall charge, so I didn't use the brackets. But this one, we do use the brackets and put the charge outside the brackets because it is charged.